Okay, good afternoon. As usual, somebody can tell me if you can hear. If you can hear, write on the chat. Okay. Okay, so you should also see the screen. Today we will resume from where we left yesterday. Yesterday we started discussing Gaussian classifiers. We started discussing Gaussian maximum likelihood estimates and then we applied it to classification problems. We said we built a generative classifier. A generative classifier gives us what? Gives us a model from the class conditional density, so a model that describes typically in a parametric way. For us, we have a Gaussian model, so it is a parametric model. But in any case, a model for the Gaussian, the class conditional density, that is the distribution of the feature for each class. Then we have seen that we can combine this with an application prior, that is the class prior probability for the given task that we are considering. So it depends on the task. And applying bias rule, we can use this to compute class posterior probabilities. The joint likelihood is partly given by our model and in part by the prior probability. The model gives us a way to compute this first term, to define this first term. Then we have made an example with univariate densities and we said, okay, let's try to build class conditional densities by fitting Gaussian densities to the samples of each class. And then we have seen, once we have computed maximum likelihood estimates, how can we use this to make inference for a new sample. For a new sample, we compute the class conditional density for all classes using the maximum likelihood solution. Then from this, we combine this with the prior to compute the class posterior. And then, depending, of course, on the value of the class conditional densities and the value of the prior, we end up with a solution that tells us whether there is a higher probability of the class being male or being female, given the sample. And from the moment we said we take the class that has highest probability as the class for the sample. Then we try to formalize this a bit better. We said, let's consider a generic dataset where we have multidimensional features that we model as Gaussian densities. Well, before we model them as Gaussian densities, let's just say that we make some assumption on the model. We assume that samples are statistically independent given the model parameters, and given the model parameters, they all share the same distribution. That in our model will be Gaussian. With this assumption, we can try to infer the model for the class conditional density of each class by computing the likelihood for all the samples as a function of the parameters of the model, and then we can maximize this likelihood, which means that we write the likelihood for all the observed values as a function of the parameters. Thanks to our independence assumption, we factorize this likelihood over the single samples, and then we said once we have this factorization from the joint density, we plug in our model that gives a specification for the class conditional density. In our case, we decided a model where each class is described by a Gaussian density and each class has its own mean and covariance matrix. So for each class, we have a different set of parameters. Then the prior probability, we said it's not dependent on the parameters of our model because our model does not specify the prior probabilities. So this, when we maximize the likelihood, is irrelevant. We will find it again when we do inference, but for estimation of the model parameters, it's irrelevant. And then what we need to do is to maximize this function, which we can rewrite as maximization of the log likelihood, that is a maximization of the log density sum over the samples. In this case, where each class has a different set of parameters, it's convenient to rewrite this summation as a sum over classes of the sum of the log likelihood computed for the samples of that class. Why? Because each of these inner summations will depend only on one set of parameters. So when the class is 1, here I will have mu1 and sigma1 for all the elements of this sum. When the class is 2, I will consider all the samples of class 2, and here I will have mu2 and sigma2, and so on. And we've seen that this is convenient because we can express our log likelihood as a sum of these partial, let's call them partial log likelihoods that depend only on the samples and on the parameters of a single class, and each of these corresponds to exactly the log likelihood of a model that is a model for the samples of that class with its own set of parameters. So the maximum likelihood solution requires that we fit, if we assume that each class has its own set of parameters, we fit independently by maximum likelihood a Gaussian distribution, a Gaussian density to the samples of each class. Then we have discussed how to compute the maximum likelihood estimate for multivariate Gaussian densities. The log likelihood, here is for a single class, is again a sum over samples of the logarithm of the density. It has some constants that are not relevant, then some terms that depend on lambda, and some terms that depend on mu and lambda. And we have discussed yesterday that the solution can be given how? Well, the solution corresponds to setting the mean equal to the empirical class mean, and the same for the covariance matrix. The ML solution is the empirical covariance matrix. Now, this gives us a way to compute the parameters of the model. Other questions on this part? Okay, this is where we stopped yesterday. So now we can go on and see what we do once we have computed the parameters. Remember that once we have computed the parameters, we will want to make inference. First of all, let's try to apply this model to some dataset to visualize what happens. Before we have tried it with the one-dimensional height problem. Now let's see how the model describes samples that are two-dimensional. In this case, we have two-class problem, red versus blue, and we can find the maximum likely solution for the two classes. For the red class, the mean is somewhere here. For the blue class, it's somewhere here. I hope you can see here. And as usual, we describe covariance matrices in terms of ellipses whose axes are related to the eigenvalue, so to the spread of the axes represent the principal axis of the covariance, and their length represents the spread over that direction of the sample, so it's related to the variance over that direction. So we can see that the first model identifies a blob of points which has this kind of shape, while the blue Gaussian identifies points that are organized around this mean here. Let me do it in yellow. And they are organized with a spread that is more or less the same over all directions. Almost the same, it's not exactly the same, but almost the same. While for the red, we now see that there is a large spread along this direction and small spread along the orthogonal direction. Now remember that our original task was to compute the class for a test point. It was green before, and I hope that green you can, yes, green probably you can see it. Let's draw it in green as well. For this test point, how can we compute the class for the test point? Well, we need to compute probability of red given the sample and probability of blue given the coordinates of the samples. So given xt, this is xt. To do this, we have seen that we can apply Bayes' rule. Bayes' rule requires that first we are able to compute class conditional densities for all the classes. So we need to compute class conditional for xt given red, for xt given blue, and in this case, that's all we have. So for a generic problem, if we have C classes, for all the classes, we need to compute class conditional density for the test point. These are computed with the maximum likelihood estimate for class C. So for each class, we will have a different set of parameters. For example, for the two-class problem, we will have the Gaussian density given mu red and sigma red, and then we will compute Gaussian density with mu blue and sigma blue, and the star one, the one that I estimated from the data. And this will be the set of class conditional likelihood. Then, according to the Bayes rule, what do? I combine this with the prior. I combine this with prior probabilities. So for each class, I compute the class conditional times the prior. And then to get class posterior, I just need to divide by the marginal with respect to the classes. Notice that the marginal with respect to C classes is the sum. If I have computed the numerator here for all classes, so if I have computed this for class 1, this for class 2, this for class 3, and so on, the denominator is nothing else than the sum of all the numerators that I need to compute for all the classes. So in general, if I have, for example, a 3-class problem, I will compute class conditional given class 1 times probability of class 1. Then I will repeat for class 2 given class 2. Then I repeat for class 3 given times the prior probability for class 3. Then if I sum these three values, that's exactly, so the sum of these three, that's exactly the marginal that I need as the denominator to compute the class posterior. So if I take 1, 2, and 3, 1 plus 2 plus 3 is the marginal. So if now I take this expression and I do 1 divided by the marginal, 2 divided by the marginal, and 3 divided by the marginal, this gives me exactly the class posterior. So this will be probability of class 1 given xt. So essentially what I need to compute are these terms. Once I have computed these terms, I have everything that I need because I can easily compute the marginal by just adding this value. And if I want the class posterior probability, I just need to divide by this value. That makes sense. To transform this joint into posterior, I need to renormalize them so that they add to 1. And to make them add to 1, I need to divide them by their sum. This is exactly the operation that I'm doing. And actually, we have seen that the margin is not really important because in the end, what we will do is look at the maximum, at the class which has the maximum posterior probability. Since this denominator does not depend on the class, it will be the same for all classes. So the maximum of the class posterior probability will also be the class for which the joint probability is maximum. So once I've computed these values, I have all the information that I need to make my class assignment. But in any case, let's see how we can express this. This is the general case. Let's go a bit more in detail to what happens if I have a two-class problem. If I have a two-class problem, the two probabilities that I need to compute are these two. Probability of class being 1 and probability of class being 0. Now, if the probability of class being 1 is larger than the probability of class being 0, I will assign class 1. Then, if the probability of class 1 is lower, then I will say that the point belongs to class 0. I can cast this by considering the ratio between these two class probabilities. Now, if this ratio is larger than 1, it means that class 1 has a higher probability than class 0, if this ratio is lower than 1, then I will say that the point is from class 0. Now this is called, and here in the slides you have class H1 and H0 rather than 1 and 0, but these are just names for the class. Here in this set of slides, one class is called H1, the first hypothesis. Usually we also use true hypothesis or true hypothesis and false or false hypothesis, or 1 and 0. There are several ways with which you can describe a binary problem. If we want numbers, we will use class 1 and 0. If we want to be generic, they will be typically hypothesis 1 and hypothesis 0, or true hypothesis and false hypothesis, or directly true and false. Or when it matters, as in the previous example, we can give a characteristic. It will be red versus blue or male versus female. This is just a way to call the classes, so it doesn't really matter how you call them. Get used that depending on the task, we may change the way we call the classes. So we have two classes, H1 and H0. For example, male and female, if you want to go back to our original example. Then we can make our class assignment by computing the ratio between the class posterior probabilities. We call this R. It's a function of the sample. For each sample, we compute the two class posterior probabilities, we compute their ratio, and then we can make our decision based on the ratio. The ratio will be what? Will be between 0 and 1, then we say it's class 0. If it's between 1 and infinite, so infinite means probability of class 0 very small or up to 0. When it's 0, we assume the ratio is infinite, but for our purposes, it doesn't really matter that it's not mathematically defined. When the class posterior is 0, our ratio is infinite, which this means, in any case, class 1. So we see that we have a range of values which correspond to class 0 and a range of values that correspond to class 1. As we said for the likelihood, it's more convenient to express this quantity in terms of logarithms. Why? First of all, because here we see that there is an asymmetry. There is an asymmetry related to the fact that on the left, class 0 is defined in an interval that goes from 0 to 1, while class 1 corresponds to an interval that is open on both sides that goes up to infinite. So there is an asymmetry in how I handle the classes. If I move, and then there may be numerical problems when we want to actually compute these values. We will see that if we go through the logarithm, these disappear partially, at least. So rather than working with the ratio directly, we work with the logarithm of the ratio. Now notice that with the logarithm of the ratio, we have some interesting things. First of all, we will assign the point to class 1 when this quantity is greater than 1, which means that the logarithm of the quantity is greater than 1. So whenever, let's call this L. No, let's not call it L, let's call it Q. L will be another thing. When Q is greater than 0, we will assign class 1. When Q is smaller than 0, we will assign class 0. So class will be H0, and here class will be H1. So now we have asymmetry in how they behave. If it's greater than 0, it's assigned to class 0. If it's lower, it will be assigned to class 0. So larger than 0, class 1, lower than 0, class 0. And there is also symmetry. Now we handle the hypothesis, because if we exchange the two labels, so we call what was labeled H0 before, now we call H1, and vice versa, so we exchange the role, we see that we are, with the logarithm, we are just taking minus the value that we had with the previous ratio. So the logarithm transforms our ratios into values that are essentially behaving in a symmetrical way with respect to the two classes. So they treat the two classes in the same way as output ranges and as output ranges, let's say. Let's stop there. So it's useful to cast it as a logarithm. Then when we cast it as a logarithm, we can also discuss a bit more what our model is doing, at least for the binary problem. We said if the log ratio is greater than 0, we will assign class H1, otherwise we will assign class H0. Let's now see how this value depends on the model parameters. We can take this value and we can rewrite it in terms of the things that are computed by our model. Remember that our model computes class posterior, class conditional densities, class conditional density values, so this kind of objects. Let's express these class posteriors in terms of these values. For class H1, we have that this is the class conditional for x3, assuming that the class is H1, it's the parameter theta, times the prior probability for class H1, divided the marginal for xt. And for class H2, we will have class conditional of xt given class H2 and theta, prior probability of class H2 divided the marginal for xt. Now, this is on top of the fraction, this is below, so when we multiply these together, what do we get? Well, we need to reverse the second fraction, we get this term, we get what? We get this term on the numerator. Remember that this term here on the numerator is also corresponding to the joint likelihood. So we have the joint likelihood of xt and h1 here times divided by the marginal. And for the second class, the marginal goes on top and the joint likelihood goes below. These two are the same, so we can just simplify them. So what remains is, on top, I will have class conditional for class 1 times prior for class 1, and below class conditional for class H0 times prior for class H0. Remember that these are the things that our model computes, so these are actually the one that we parameterize in terms of the model. So this depends on our model theta. Now, these expressions are in general, but for our model, these will be parameterized by our model. They will be given by our classifier. This is what our Gaussian model will compute. While these represent, we said, prior knowledge that describes the task that we want to apply our classifier on. Now, this is a logarithm of a product of these two terms. So we can split into a sum of logarithms. We have a sum of logarithms. The first part contains the ratio between class conditional densities, and the second part, the ratio between the class prior probability. The first term is called log likelihood ratio. Why? Because these are the likelihoods for the hypothesis H1 and H0. This is what our classifier will compute. The second part represents what is called prior log odds. All log odds means that we are computing the logarithm of the odds, so the ratio between the prior of the class being 1 divided the prior of the class being 0. And if we have a binary problem, remember that this must be true. So if we say that the prior of class being 1 is pi, then the probability of the class 1, the prior probability for class H0 is 1 minus pi. So for a binary problem, we will describe the prior probability in terms of the probability of class 1, typically, the true class, the one that is on top of the numerator. And then the other class will have a probability 1 minus pi. So we can express the log likelihood ratio as, we can express our log posterior ratio as a sum of a log likelihood ratio that depends on class conditional likelihoods plus the prior log odds that depends on the application prior probability. The second term represents the task, so it gives us information that is related to the specific environment where we will apply our classifier. We made yesterday the example. Prior probability describes the probability that I will get a sample of that class. If I take pictures and I'm a cat lover, then probably my prior probability for cat is large and my prior probability for dogs is small. If I'm a dog lover, it may be the opposite. I may have that the prior probability for dog is larger. In any case, this depends on my prior knowledge on the problem. The other term is what our classifier should focus on producing. So what we would like our classifier to give. If our classifier gives that term, then we can easily combine it with prior log odds. We can even make a further step to show how these two depend. The decision was based on what? We said that the decision was if the ratio was greater than 1, assign class 1. If the ratio was smaller, assign class 0. When we move to the log, remember this is the log of the class posterior probabilities. If this is greater than 0, then it means that this fraction is larger than 1. So class 1 has a larger probability, we'll assign class 1. If this is smaller than 0, then we will assign class H0. So essentially our decision corresponds to comparing the log posterior ratio with 0. Now let's write this rule, that is the rule that we use to make classification, in terms of the log likelihood ratio. The log posterior ratio has this form. So essentially we compare this expression with 0. And then if it's larger than 0, class 1. If it's lower than 0, class 2. But when is this expression larger than 0? Well, it's larger than 0 when the first term is greater than minus the second term. So whenever this term is larger than minus log of pi divided 1 minus pi, it means that log ratio is greater than 0, so we assume, so it's class 1. If this value here is lower than minus log pi divided 1 minus pi, then log r will be lower than 0, we assign class H0. So we can cast the problem as taking our log likelihood ratio and compare it with a threshold t. What is this threshold t? Is minus the prior log odds of our application. This behaves like a score. We call it S of x, but it's a score that is a strong interpretation. It's a score that represents a log likelihood ratio. And here we have a threshold. So again, we can cast the problem as computing a score and compare it with a threshold. The score represents what? Well, in general, it's a number that gives support towards some hypothesis. When the score increases, it means we increase our support for class H1. When the score decreases, it means that we increase our support for class H0. If this is the score, here we will have a strong support for class H1. Here we will have a strong support for class H0. Around 0, our model will be quite uncertain on which is the correct, on which is the best hypothesis. Then, to decide, we need to combine it with the application information. So, based on the value of the application information we will decide. Notice that if the class have the same probability, so probability of class 1 is equal to probability of class 0 a priori, then this becomes 0. So if the classes have the same prior probability, we cut exactly at 0. When the score is larger than 0, we will assign class 1. If it's smaller, we will assign class minus 1. But depending on the value of the class prior probability, we may need to move our threshold. For example, if my prior probability for cat is 0.9, it means that I need a much stronger likelihood from the classifier that suggests that the dog hypothesis is true before I move to the dog hypothesis. So in this case, I may end up labeling whatever lies in this area, and here this blue line is minus logarithm of 0.9 divided 0.1. Whatever lies in this region will be labeled as class 1, even if the score is negative, because I have a strong prior evidence that the picture will probably be of a cat, and whatever is lower than that threshold will be labeled as class blue, so for example dog. So the classifier will give me a score that measures the strength of the hypothesis, and then I will combine it with the strength of my prior beliefs on the hypothesis. The prior represents my prior belief that a class will be one or the other. Combining these two, I will get my decision, my answer to which label I should apply to the class. And we will see, probably next week, we'll start discussing when this is optimal, under which sense this is optimal. But for the moment, we just say because that's the highest probability, so we expect it to, we have a higher chance of being correct. According to our point of view, we'll see. As we said, okay, this is exactly what I said. We will see that class posterior probabilities alone are not sufficient in many cases to make optimal decisions, but for the moment, we said that we assume that they are, so what we said is correct. Now we can ask ourselves, okay, if our decision rule corresponds to comparing a score with a threshold, what kind of decision rule we obtain? First of all, we observe that this is similar to what we had with LDA. With LDA, we built a classifier where we were computing a score that was compared to a threshold. In this case, in the case of generative models, this score has a probabilistic interpretation. It's a log likelihood ratio. So the threshold is defined by the probability theory. We will show that the threshold that we use is optimal, and this is the threshold that we should use. So having a probabilistic interpretation allows us to decide based on the application which is the threshold that we should use. If this represents a log likelihood ratio, the optimal threshold will be the threshold that depends on the prior probabilities. And we will see also on other things once we make it a bit more, when we extend the problem a bit. While for LDA, we didn't know how to select the threshold, we now have, for this model, when it's a log likelihood ratio, we have a way to decide the threshold. This is the log likelihood ratio, the output of our model. It's a ratio of class conditional densities, a ratio of class conditional likelihoods. This will be minus the prior log odds. Now, it may be interesting to observe for different values of t. Remember that t is a parameter of the prior, so when we change our application, we will change the threshold. We can, for a given threshold, which corresponds to a given prior probability, ask ourselves what is the decision boundary. This is the decision rule, which means that we will have our space that will be split in regions. This boundary will be where the log likelihood ratio is exactly equal to t. Then on some side of this boundary, the log likelihood ratio will be greater than t. On the other side, the log likelihood ratio will be lower than t, which means that from a geometrical point of view, the set of points described by log likelihood ratio equal to t represents the boundary that our classifier puts between the two classes. Whatever is on one side of the boundary will be labeled as class 1. Whatever is on the other side of the boundary will be labeled as class 0. So this will be H1, and here I will label as H0. So any sample that falls in this region will be classified as H0, and any sample that falls in this other region will be classified as H1. So it's interesting to observe which kind of decision boundaries we get from our classifier. As I said, we need to compute solutions to log likelihood ratio, so the score, equal to the threshold that defines our boundary, our decision rule. The decision rule is compare the score with the threshold, and if it's greater, we assign class 1, otherwise we assign class 0. So let's see what is the boundary of these regions. The log likelihood ratio for our model is what? Well, we remember that we were doing Gaussian models. So our idea was, once we have computed our Gaussian models, we need to compute the log likelihood ratio, which is expressed in this way. But these are the Gaussian densities computed with the maximum likelihood solution of the parameters. So this can be expressed as the normal for the test example using the parameters of class H1 divided the normal density computed with the parameters of class H2, and then taking the log of this expression. Now, what kind of decision rule do we get? Well, we need to compute this logarithm, put equal to t, and solve for x. If we solve this as a function of x equaling this to t, what we get is the decision boundary for our classifier. So we compute for our two classes, class 1 and class 0, the log density at x, and we want to set this equal to a threshold t. Now, what kind of expressions do we get? Well, we need to see what is the expression for the log likelihood. For the log likelihood, we go back, and we have, if you remember here, the expression for the log density of a Gaussian density. So what we have is logarithm of, let's write it like this for simplicity, these two terms, mu 0 and sigma 0, which we write as log of the first minus log of the second, of the denominator. Again, rules of logarithm. Each of these can be expressed by simply taking the expression that we have here, and as we said, using precision matrix, this gives us easier to manipulate expressions. What we get is that each, sorry, this is not a fraction, it's minus that continues on the other line. For the first one, we will have constant minus plus 1/2 log determinant of lambda 1 minus 1/2 x1 minus x minus mu1 transpose lambda x minus mu1 minus the second one, so let's write plus minus a second constant, which actually is the same constant because it's the same dimensionality, minus 1/2 log determinant of lambda 0 plus, in this case, 1/2 x minus mu 0 transpose lambda 0, here it's 1, here it's 0, x minus mu 0. Remember that I have minus the log density. If I develop this expression, we see that these were quadratic forms. So if I develop the squares and I put all the terms together, so I rearrange the terms, I can see that what I can get is an expression of this kind, where this A, B, and C depends on the parameters of the two Gaussian densities. This is what we discussed yesterday. This is a quadratic function in X. Decision rules look like solutions to this equation. Which kind of solutions we have? Well, it depends on the value of t, it depends on the eigenvalues of A. We can have solutions that look like ellipses, hyperbolic surfaces, or in some corner case, parabolic surfaces, or we will see linear planes in a limiting case. But in general, this will be quadratic functions, so ellipses and hyperbolas. We have also hyperbolic shapes because while when we do Gaussian densities, the covariance matrices have all eigenvalues that are positive. Here, this A matrix is a difference of two precision matrices. So the eigenvalues of A may all be positive, but they may also have different signs. So I may have one is lower than 0 and the other one is greater. So I may have hyperbolic-like shapes. It's not necessary that all of them are positive, because it's a difference between two precision matrices. Which means that depending on the model parameters, I end up with decision rules that have this shape. For the example that we have in the slides, we have hyperbolic separations. Why do I have many surfaces here? Because each surface, each pair of surfaces actually, so purple goes with purple, blue goes with blue, the red, well, you don't see them, but the red would be somewhere here, the other red ones that you don't see. So here you would see if the plot went on something like this. Correspond to what? Each of these values correspond to the solution of log-likelihood ratio equal to a prior log odd. So, to a different threshold. This is the threshold T. For each threshold, I get a different solution. So, if I set the threshold to 0, my boundaries will be these lines. With a threshold 0, my classifier will say that whatever is here is assigned to the red class, and whatever is outside is assigned to the blue class. Notice that even things that are far from both classes here have a strong effect on the blue class. Why? Because the blue class spread along this direction is much larger than the red class spread along this direction. So if I'm very far from the training set samples, it's true that this is an unlikely point for both classes, but it's even less likely for the red. So it becomes a bit more probable that this is an outlier from the blue class rather than from the red class. The farther I move, the more it's likely that this is an outlier of the blue class rather than the red, because the red spread is smaller over the vertical direction. If I change my threshold, I change the boundaries. If my threshold becomes -8, it means that my prior belief is that it's more likely that the points come from the red class, which means that I need a stronger counter evidence from the score to decide that the point is from the blue class. If my threshold is -8, whatever is in this region of space will be labeled as red, whatever is outside will be labeled as blue. Notice that this is not inconsistent with our dataset. Our dataset has a different empirical prior. The empirical prior of the dataset here is probably 0.5, so threshold equal to 0. But if my application is a threshold -8, it means that I have a very strong prior hypothesis for the samples being from the red class, which means that if I were to use a frequentist interpretation and draw a number of points that is proportional to the class prior probabilities, I will probably end up with a solution that looks like this. So even in this region of space here, I will see more red points if the number of red points is scaled to the prior probability, which means that, and this is frequentist hypothesis, frequentist interpretation. With the Bayesian interpretation, it's just the prior probability is my prior belief. If I have a strong belief that the sample is red, I need an even stronger counter evidence from the log likelihood ratio to go against my prior beliefs. Frequentist interpretation, if I build a dataset which has the same prior as the application prior, I will see a predominance of red points in this class, because actually there will be many more red points overall than blue points. So even if this is a region with low density from the point of view of the red class, if I multiply a low density region by a large number of points, I will still get a large number of samples with respect to the blue class. So this region will be still assigned to the red class. The opposite is true with a weak prior. If my prior says that class blue is more likely a priori, then whatever is in this region will be labeled as class blue, and whatever is here, and probably, as I said before, here will be labeled as class red. And as I change my threshold, you see that the boundaries move towards the region of one class or the other. So I have different boundaries that depend on the application prior. So the log-likelihood ratio gives me the score, and then the application defines which of these all possible separation surfaces that I can have for my classifier will be the one that defines where the classes change. So the class boundaries. Other questions on this part? Sorry, just a second, I lost. Okay, now for multi-class, we already said almost everything that there is to say. For multi-class problem, we have less insights on what's going on, so we will not have something that behaves similar to a log-likelihood ratio, but we can still build something that behaves like a score vector. For multi-class problem, we said our goal is to compute class posterior probabilities for all the classes. And we have seen that the class posterior probabilities are proportional to the class conditional times the corresponding prior. Why? The proportionality factor is 1 over the marginal. The marginal depends on the sample, but here we are looking at this as a function of the class. So the marginal does not depend on the class. So as a function of the class, this is a constant, so it's a proportionality factor. Here you have to look at this as a function of the class. So this proportional is as a function of the class. Optimal decisions, we said, are obtained by computing the class that maximizes our class posterior, which corresponds to maximization of the joint likelihood. Written in terms of logarithm, we have maximization of the logarithm of the class conditional plus the logarithm of the prior. Which means that to compute the solution to our classification problem, multiclass, we can do what? We can, for each class, compute the vector of class conditional. And let's write just H1, H2, H3, and so on. This will be a vector with k elements. We call this a score vector for x. In this case, we have a score vector which contains one value for each class. Higher values for a class means that the classifier favors the corresponding hypothesis, but to make our assignment, we don't look just at the score, but we need to combine this with the vector of prior log odds, of prior log probabilities. We combine these two vectors, and then we take the max along the value of this vector. So we have a vector of scores that we combine with a vector of prior probabilities, log prior probabilities. We combine these two, and then we take the maximizer of this vector. The entity that the hypothesis H that has maximum value will be the one that we assign. So also in this case, we have a score vector that depends on the classifier that we can compute independently of our prior probability, a vector that contains prior information, and combining the two, we can get our optimal decision. Also in this case, we can show that the fact that the log densities are quadratic forms of x gives us the shape of the different boundaries that, of course, depend on the prior probabilities. In particular, here you have the image of a three-class problem, contains these three classes with uniform prior, so the prior for the classes is taken to be 1 out of 3. And you see in the image what? These bright parts are the boundaries between two classes, so the places where my labeling changes. In this region, my label is red. Then when I reach this point, it will switch to green. When I reach here, it will switch to blue. If I have blue here, then again, when I reach this boundary, I will switch again to green. So these are the regions that define the boundaries between the classes, which are also piecewise quadratic. So each of these is a piece of a quadratic boundary. Where the boundaries are depends on the prior probability. So if I make the prior probability for the class red smaller, probably these boundaries will change in a way that looks like this. They will move towards the red class. And only this region will be labeled as red if the class prior probability for the red class becomes smaller. Of course, if we have 3 class prior probabilities, 2 of them are independent, so see all the effects is not easy graphically. What you see here is also a graphical representation of the class posterior probability for a sample. How? If you take a point here and you look at the color of the corresponding pixel, the color of the corresponding pixel, so you take the pixel and you look at this color, the color of the pixel encodes the class prior probability. Remember that an image has 3 colors, the red, blue, green, and blue channel. The intensity of these colors is proportional in this image to the class posterior probability. So when the point is red, it means that the class posterior probability for the class red is very high. When the point is green, it means the class posterior probability for green is close to 1. When it's blue, it means it's close to 1 for the blue class. On the boundaries, here you see yellow shape, yellow color. The prior probability for blue is, the posterior probability for blue is small, but I have more or less equally probability for the red and the green class, and they are around 0.5 in this region. Here, where all 3 intersect, we will have that the class posterior probability for the 3 classes become more or less the same. So the color intensity here represents the posterior probability for the corresponding class, according to the classifier that was trained by maximum likelihood using the samples that you see in the image. Okay, questions up to here? Okay, now this is essentially the idea behind the Gaussian model. Fit one model for the moment we have seen to each class, and then use that for binary problems to compute a logarithmic ratio that then we compare with a threshold, or for multi-class problems, compute a vector of class conditional densities, then combine it with a vector of prior log probabilities, and then look at the maximizer of this vector to find the class that you want to assign to your sample. Now, the limitations of this model, well, first of all, it needs to be, we require that the data can be well described by Gaussian distribution. For example, if we have a data set where the class points behave like this, then fitting a Gaussian density here will not do a good job. The density model will have a low density in regions where I have lots of samples, and we have high density in regions where we have low amount of samples. So it will not be a good fit for our data. Sometimes this is not a problem, sometimes it is. We will discuss a bit better when we discuss the project part of the next laboratory. Now, the problems that we analyze in this part of the lecture are related to the problem of estimating a large number of parameters, to the risk of overfitting of this model. This model requires for each class that we compute what? A mean vector, which has a dimensionality equal to m. So we have m times k mean vectors. In the covariance matrix sigma, for each class, this is dimensionality n times m. So if I have k classes, this is the number of parameters that I need to compute for the covariance matrices. If I have a dataset with n m-dimensional samples, these are the values that I can use to build estimates. Now, this means that typically I don't need a large number of samples to compute the mean. Why? Because typically, if the number of samples compared to the number of parameters is roughly few tens of times more, then I can reliably estimate the mean of the class. So I need to have few tens of points for each class to get a good estimate of the mean of the class. But for the covariance matrix, to fill of the values in a reliable way, I would have to have few tens times the dimensionality of the dataset itself. So times the dimensionality of the input space, because this grows quadratically with the input space. Which means that if, for example, I have, let's say, a problem, image recognition problem, I have 100 images, no, 10,000 images per class, but my classes have 1,000 pixels, my covariance matrix will have each 1 million samples. And now I need to estimate these 1 million parameters. I will need to estimate these 1 million parameters out of what? 10,000 images, each with 1,000 entries. So the ratio of the parameters with respect to the numbers that I have in my training set is not very large. So while the mean usually it's sufficient to have few tens of samples to estimate them reliably, we need more to get good estimates of the covariance matrices. Actually, notice that it's not true that they are the square of the dimensionality. It's actually something that is proportional to the square of the dimensionality of the input space. Now, when this is a problem where we have large dimensional features. This is also a problem when we may have low dimensional features but many classes. For example, if you want to make a face recognition task, what you will have? You will have images of people. Let's even say that you make very condensed information. So you take your image, you are able to apply PCA or whatever else, and you can condense in few tens of dimensions the information of the image. So each sample, each image will be represented by 100 dimensional samples. These are already small numbers compared to reality. What is the big problem? Is that for person 1, you may have just 3 pictures. Then maybe you have 4 pictures for person 2. Then maybe you have 2 pictures for person 3. Now, if you want to build a Gaussian model for each of these classes, if each of these classes has its own covariance, its own mean, and its own covariance matrix, you see that even if I have small dimensional samples, with just 3 samples, I will never get a good estimate of the covariance matrix. Actually, my covariance matrix will be singular as long as I have more than 2-dimensional samples. I need at least, to get a non-singular matrix, if my dimensionality of the space is m, I need at least m plus 1 elements. Otherwise, my covariance matrix will even not be well defined anymore. But this is the typical use case when you have lots of classes and few samples per class. So how can we address these problems? One problem is we have some good amount of samples per class, but the feature dimensionality is very large. So let's say each image is 1 million parameters. If we work with 1,000 by 1,000 picture, each picture can be characterized by 1 million parameters. So my covariance matrix should be 1 million times 1 million. How can I reliably estimate these amounts of data? Or problem 2, I have maybe even lots of samples overall, but this corresponds to a large number of classes and few samples per each class. Here, even if the dimensionality of the input space is small, still I cannot get good estimate of the covariance matrices. Now we will see two possible models that introduce simplifying assumptions that may allow, under the assumptions that this model, the additional assumptions of this model, to address this kind of problems. The first is called naive classifier. A naive classifier makes additional assumption on the features. What is the assumption? The assumption is that the class conditional features can be described as being independent. What does it mean? That given a class, and it's important that this holds given a class, so it's not true for the feature vector on its own, but it's true only given a class. If I have a random vector, and now I use square notation to identify the components of a vector, so this is a vector with component 1, 2, and 3, it says that the component 1 of the vector is independent of the component 2 given the class. So if I know the class, then the components are independent. What does it mean? It means that if they are independent, I can factorize my class conditional density as a product of, in this case, univariate densities, but we could do models that are a bit more complex, but in this case of univariate densities, one for each component. For example, we said that we were considering the height problem where we were identifying male and female based on the height. Then we said we can make a problem where we have the height and the weight of somebody. So we may have for the first person weight and height, then weight and height, then weight and height. Now this will give us what? If we were to plot the samples for male and female classes, we will end up with something where the males will be somewhere here and the females somewhere here. So they will be on average less tall and less weight. If we look at the samples of one class only, then we would look something like this. So we will see that the height and the weight are somehow correlated. Not perfectly, in the sense that I can have somebody who is tall and very thin, I can have somebody who is small but weighs a lot, but there is some correlation between the features. The naive models the data assuming that these two factors are independent. So they say once I concentrate on one class, let's say female class, then the height is independent of the weight. The way the height changes does not influence the way the weight changes. Now, of course, this is not true. We know that this is not true in reality. But if this is true enough in the sense that the independence assumption is not the dependency between the features is not very strong, then this can be an approximation that simplifies greatly the computation. So if, for example, I have a population where the height and weight for the same class are not strongly related but can be considered almost independent, then the naive Bayes model will simplify the computations. Why? Because essentially it doesn't need to take into account correlations between features. If my features are independent, then remember that independence implies that the correlation is zero, which means that I already know that there is no, when I make the assumption, I'm forcing the model to avoid computing correlation. But remember that the elements outside of the diagonal of the covariance matrix represent in some way, measure the amount of correlation between the different features. If I know that this should be zero because my model wants them to be zero, I don't need to estimate these quantities anymore. And this simplifies my computation. Now, again, this is the intuition, but formally, what I say is that I can factorize my class conditional density over features. And I can apply this on the Gaussian model, but I can apply this assumption on any distribution. So this can be applied to any class condition. Here you see that I didn't make any assumption about the model being Gaussian. The Gaussian naive Bayes model assumes that for each component, the class conditional density for that component is described by a Gaussian component. So the class conditional density for the height component of my feature vector, given for example male, will be described by a univariate Gaussian, let's say 174, given the male mean for the height parameter and the variance for the mean class for the height parameter. And the weight component of my feature vector, let's say 80, will be another Gaussian, univariate Gaussian, with a mean, this is the mean for the male class for the weight, and the covariance matrix, this is actually a variance because it's one-dimensional. This is the variance for the weight class. And then the feature vector 17480, given the male class, will be obtained by multiplying these two. The density for the height, this h here is for height, times the density for the weight, which you see act independently. And this is my model. Notice that now I have one scalar for the weight, for the height, for the mean, one scalar for the weight mean. So I have two parameters for the means, but for the variance I have also two parameters only. If I had estimated a two-dimensional multivariate Gaussian model, my covariance matrix would be a 2 times 2 matrix with three free parameters, the two variances and the covariance between the height and the weight. So my model is defined by defining, in this case, univariate densities. So each density has only one parameter per each for mean and one parameter for variance for each component of my feature vector. Then we can ask ourselves how we do the estimate. We do the estimate again by maximum likelihood. We need to write the likelihood. The likelihood is the product over samples of the joint density. Product over sample of the joint density for our feature vectors. Given the parameters, let's just write the parameters. But this joint density is what? This joint density is on its own a product over the components of the feature vector. So it's a component over the feature vectors of what? The parameters that relate to that component. But each of these is a Gaussian density with one mean and one variance that depend on the class and on the component. Going to the log, this product becomes a sum. So I have a sum over samples and then a sum over components. The sum over samples, as before, I cast it as a sum over classes followed by a sum over the samples that belong to that class. And this is the log density for the samples of that class, which is itself a sum, comes from this term, of univariate log normal densities. And then I can rearrange the sum. I bring this sum outside and I get this expression. This is a sum over components of what? This expression here. What is this expression? Well, let's imagine I have my data matrix with n samples that are d-dimensional. Each of these elements in the sum corresponds to taking one feature, so one row of my data matrix, extract it from the data matrix, treat it as if it was a set of feature one-dimensional features, and then this would be a Gaussian model, the likelihood of a Gaussian model for that part of the matrix. So the naive Bayes, I can see it as I'm slicing my data matrix with respect to its components. So I'm considering different features independently. And for each feature, I'm building a Gaussian model that is one-dimensional Gaussian model, one per feature. And then what I get is that for each component, my solution is the mean of the values of that component. So I get my component J, I extract it, I treat it as a data set, I slice it into classes. Well, first I slice into classes if you want. It's the same. You can slice it before or after. Okay, so that's what I was doing. I take my row, I slice into classes. For each class, I compute mean and variance, empirical mean and variance. These will be the parameters of the Gaussian that will describe this feature for this class. So let's say these are class 1, class 2, and class 3. I will get one Gaussian that describes this part of the data, one Gaussian that describes this part, and one Gaussian that describes this part. This will be the set of parameters of my model. Now, how do I get a description of the class 1, class 2, and class 3? Well, the density for class 1 will be the product over the components of the test vector x that I want to classify of the Gaussians that I have computed for each of the different features. So when I have a test vector and I want to test it against class 1, I will slice it into its components. For each component, I will compute the corresponding density value over the Gaussian that was associated to that component for class 1. I will multiply all this together. This will give me the density for that sample for class 1. We will actually do it in the log domain, but that's not a big issue. This is what this expression is doing. I take my x vector, its components. For each component, I compute the density using the parameters of the Gaussian that is associated to that class and that specific component, and I get the result. Now, for the Gaussian model, we can show that the result of all this process is again a multivariate Gaussian density. So the result is the same expression as a multivariate Gaussian density, where the mean vector corresponds to taking the mean of the single components of that class, and the covariance matrix corresponds to the values that I have estimated from the covariance for the single components. Now it happens that if we look at how these matrices are built, this is nothing else than the empirical mean. Again, once more, it's empirical mean of the class C, and this is a matrix which is diagonal, but this diagonal corresponds to the diagonal of the maximum likely solution of the MVG classifier. So actually, we can show that for the Gaussian model, and I say Gaussian naive Bayes model only, if I change the distribution, this does not hold anymore. For the Gaussian model, the naive Bayes corresponds again to a multivariate Gaussian, where essentially I force all covariances to be 0. Remember that we said that independence implies covariance 0. For Gaussian densities, the opposite is also true. If I have Gaussian distributed random variables and the covariance is 0, then they are independent. And this is why this holds. Naive Bayes assumes independence, which for Gaussians corresponds is the same as saying covariance is 0. So the naive Gaussian model for the naive Gaussian model computes a covariance matrix that contains only the variance terms and assumes that the covariance terms are all 0. Again, this last part only when I'm working with Gaussian densities. It's not a general case. If these were T distribution, students T distribution, then the product would not be a T student distribution anymore. So it will not hold in general. But for the naive Bayes, this shows us that the naive Bayes model, Gaussian model, corresponds to a Gaussian model where the covariance matrix is assumed to be diagonal. So for us, it will be simple because we will just take our multivariate Gaussian model estimate just the diagonal of the covariance, and that will be the solution. Now, since the diagonal, the covariance is diagonal, we can look at what happens to our decision boundaries. In this case, our decision boundaries will again be elliptical or hyperbolic shapes. In this case, you can see that if I apply naive Bayes to this model, these are elliptical, with the axis aligned with the principal axis. Why? Because if I try to compute the log-likelihood ratio, I will see that the matrix A that controls the quadratic term will be diagonal if I have a naive Bayes model for both classes. So the eigenvectors of this will be aligned with the principal axis of my space, which means that my decision boundaries will be aligned with the principal axis. What is naive Bayes trying to do on this model? Is trying to fit a Gaussian to the red class, which is constrained to be diagonal, and the diagonal covariance matrix means that the axes of the covariance matrix are aligned themselves with the principal axis. So it's trying to fit a covariance matrix the best it can, with the constraint that this axis must be aligned with the principal axis, and then it's trying to do the same with the blue class. Now, it cannot do a perfect job here because we have seen before that the covariance matrix of this data is oriented in this way. So the principal axis of the multivariate model are not aligned with the axis of the space. So naive Bayes is introducing an approximation. It's trying to figure out what is the best matrix that I can use to fit, that I can fit to the data under the constraint that it must be diagonal. And from this, I get my decision rule. For multiclass, again, it's similar. Last model that we see, and then we stop here. We will say a few more words next week, but these are not necessary. They will not be necessary for the laboratory, or maybe I will say a couple of words before the laboratory. The second model that we assume solves the other problem, the problem where we have lots of classes, but few samples per class. How? Well, it solves the problem by making another assumption. So it works well if this assumption is correct. It assumes that even if I have few amount of samples per class, all these classes have the same spread. So they can be represented by a single covariance matrix. Why is this? Well, this makes sense. For example, if you have images, you can imagine that the mean of the space of the samples of each person represents the person, and the spread represents the influence of external factors on the image. If you take an image of a person, you may have different lighting, you may have different backgrounds, you may have different cameras. All these affect the resulting image. But you can imagine that many of these things that affect the resulting image do not depend on the person. So they will affect in a similar way images of different persons. So for example, the difference due to illumination will be similar for pictures of different people. So we can, as a first approximation, assume that each picture is obtained by taking an average picture for that person and adding some noise term that does not depend on the class. So it does not depend on the person that is depicted. If you assume that the noise term is Gaussian, this corresponds to assuming that the class conditional density for each class is again a Gaussian, but these Gaussian each have their own mean, so each class will be described by a mean vector, but the covariance matrix that represents the spread, as usual, with respect to the class mean, will have the same form for all the classes. So all the classes will have the same spread. Now, where do I gain? I gain that if I ask all these classes to have the same spread, even if I have few samples for each class, if I have enough classes overall, I can combine the computation that I get from each class about the spread to try to estimate what is the global spread. So if the spread is similar for all classes, I can imagine that if I compute, let's imagine I bring all these samples in the same center, then they should have the same spread. So I can imagine that if I put all the samples together, then I can get from the pooled set of samples a robust estimate of the common spread of the data. So, from a point of view of parameters, I have only a covariance matrix for the classes, so the number of parameters is m squared, but it's not multiplied by the number of classes anymore. So we have much fewer parameters. As in the naive Bayes. In the naive Bayes, we had m times k for the means, but also m times k for the covariance matrices because these were diagonal. So the naive Bayes reduced the number of parameters with some assumption. The tied model will have, again, m times k parameters for the mean and just m squared parameters for sigma. So you see that this does not depend on k here. The multivariate Gaussian classifier had what? N times k for the mean and m squared times k for the covariance matrix. So you see naive Bayes drops an m, while the tied model drops the k. So I reduce the number of parameters. Of course, these models work well if my assumptions are reasonable for the data. Now, how do we estimate the boundary parameters? By maximum likelihood. Issue is that, and I will not do the steps, but the issue is that for the maximum likelihood parameter, once we tie the covariance matrices, we get this expression. We cannot factorize the problem over the different classes anymore. This parameter is shared by all the classes. So here I would have a sum where the internal term, the internal likelihood that refers to each class, depend on the same parameters, so I cannot independently maximize these terms. I need to work with the original expression for the likelihood. So I will need to write this likelihood as a function of mu c's and the sigmas for all the samples. So do all the developments that I need to do in a similar way as what we said we can do for the multivariate Gaussian model. And I would end up with a solution that shows that the parameters depend on all the samples of the classes. For the mean, we still recover, we have one mean per class, so it shouldn't be too surprising that we get once more the empirical class mean. But for the covariance matrix, now we get this expression that depends on the samples of all classes. It's a sum over classes of what? Here I consider the sample of each class and the computer xi minus mu c times xi minus mu c transpose. Now, I hope that you remember we already saw this at some point. So I will rewrite it in this way. And C is the number of samples for the class C. I hope that you remember what this is. We call this, well, this is the covariance matrix of one class, and we called this within class covariance matrix when we were doing LDA. So the solution for the tied model is exactly the within class covariance matrix of LDA. We can look at the log likelihood ratio that we get, and then we will see the parallel with LDA in a moment. If we look at the log likelihood ratio, we have that the covariance matrices are the same. Remember that the log likelihood ratio had this form where this A was, no, I don't remember it was minus or plus, but I think minus lambda 1 minus lambda 0. But now, for a binary problem, these two are the same, so A is 0, which means that this term disappears in the expression for the log likelihood ratio. The log likelihood ratio looks like what? Log likelihood ratio is equal to x transpose B plus C. So it's a linear function of x. Remember LDA. LDA, this was the score. Here, our score is x transpose B plus C, where B is given by this quantity and C by this term. Which means that we have what? Now we have a binary classifier. Decision boundaries are obtained by solving this expression, but this expression is the equation of a plane. A plane that defines the boundary between the two classes. The threshold defines which among these parallel planes I will be using for my classifier. The higher the threshold, the more I move towards the red, inside the red class. As before, if my threshold is 0, this will be assigned to class 0 and this to class 1. In terms of the model, it's trying to fit a Gaussian model in a way that does an average of the class covariance of the two classes, weighted by sample average. We have seen this with the within class covariance. Last thing, and then I stop and start the next laboratory. It should not surprise, I hope now, that this model is actually related to LDA. When we saw LDA, we saw that we were looking for a direction W by maximizing this quotient, and we showed that a direction W for a binary problem would have the form SW minus 1 mu 1 minus mu 0 for a binary problem. And our classification rule became compare this with a threshold, and we said we will see what the threshold would be. Now, if we look at the classification rule of the Gaussian model, or tight Gaussian model, this B is what? Is exactly lambda mu 1 minus mu 0. But this lambda is exactly what we called SW minus 1 when we were computing LDA. Sigma is SW, so the inverse of sigma is SW minus 1. So our Gaussian model does what? Computes this quantity and then adds C, this constant, and then compares this with a threshold. Or if you prefer, computes X transpose lambda mu 1 minus mu 0, and then compare it with T minus C. We will not cast it in this way, but we want to see the relationship with LDA, so we can represent it in this way. LDA was doing this. So now we know what is the value that we should put here. LDA can be seen as a way, as a tight Gaussian model where we didn't know how to put the threshold, but the kind of decision rules are exactly the same. Indeed, what we didn't say when we discussed LDA is that LDA assumes that all classes have within class covariance that is the same, and LDA is indeed an application of the multivariate Gaussian model to a binary classification task. So LDA as a classifier is a special case which does not give a probabilistic interpretation to the score of the tight Gaussian model. The tight Gaussian model is an extension of LDA in the sense that it will provide the same kind of decision rules, but will also give a probabilistic interpretation to the score as a log-likelihood ratio, which means that it also tells us which is the threshold that we should use to decide on the class boundary based on the application prior. And I think we stop here for today because we are already 2 minutes late. For what we need for the next laboratory, that's all. Okay, questions? Okay, then I will close this one and reopen it for the next turn.